Hi students, today we are going to see how to calculate the magnetic field due to a toroid. What is a toroid actually? Toroid means you have taken a solenoid. That is, this is a solenoid. A wire wound in the shape of a helix is known as a solenoid. Then if you bend this solenoid in a circular shape, you will get this particular shape, and this is how we make a toroid. That is, solenoid is bent in a circular shape, so it will become, after bending the solenoid into the circular shape, you will get a shape like this. So this is how we make a toroid. Then now we are going to find the magnetic field due to a toroid, and here we are considering three cases. That is, we are trying to find the magnetic field at 3 points. One is a point which is inside the toroid. This is the point which is inside the toroid, and we also find the magnetic field within the toroid, that is at this point. And we also try to find the magnetic field at a point outside the toroid. That is, we are going to find the magnetic field at this point and here also at the point which is lying outside the toroid. Okay, then let's see how we calculate the magnetic field due to the toroid. And we use our Ampere-Circuital law to find this magnetic field due to a toroid. Actually, it is the application of Ampere-Circuital law. What is Ampere-Circuital law? The line integral of the magnetic field around any closed loop is equal to mu0 times the total current flowing through that loop. We are going to use this law to find the magnetic field due to a toroid. Here, this is the figure which is given in our textbook. This is actually the sectional view of a toroid. Both are actually the same. Here, this cross sign represents the current entering the loop, and this dots represents the current leaving the loop. So this is the sectional view of the toroid, and both are same. And here we try to find the magnetic field at a point which is lying inside, within, and also outside the toroid. So we can use this sectional view of the toroid for finding out the magnetic field. First, let us find the magnetic field at a point which is lying interior to the toroid, and I will consider a point P which is lying interior to the toroid. And in order to find the magnetic field at this point, first of all we have to consider an Amperian loop. And first let us find the Amperian loop here. For that, the Amperian loop is a circle which encloses that point P, and let us take that distance from the center of the toroid to the point P as R1. So here the magnetic field is B1, and this dotted line represents the Amperian loop, and from the center to that point P, the distance is taken as R1. Here you can see that when you consider this Amperian loop, that loop does not contain any current. It encloses no current. No current is passing through this Amperian loop. So I equal to 0 here. For that loop, you can take I to be 0. So by using Ampere circuital law, we can write line integral of the magnetic field, that is closed integral B dot dl is equal to mu 0 into I. But here I equal to 0. Within that loop there is no current, so I equal to 0. I equal to 0. So what happens? Here we have taken B1 as the magnetic field. So it will become closed integral B1 dot dl is equal to 0. But we know dl is not 0, it's a length. So B1, the magnetic field B1 is equal to 0. So 4 points which are lying interior to the toroid, the magnetic field is equal to 0 because that loop does not enclose any current. Okay. Now let us find the magnetic field 4 points inside the toroid. Inside the toroid means that point lies within the toroid. That is, that point lies within the toroid. So let us consider a point. Let us take the point as S. That point lies within the toroid and the distance of that point from the center is taken as R. So to find the magnetic field, we have to consider the Amperean loop. And here we know Amperean loop is a circle of radius R. Then let us take capital N be the total number of turns. The toroid has different number of turns, and let us take capital N as the total number of turns. Then to find the magnetic field, we use Ampere's circuital theorem, that is closed integral B dot dl is equal to mu 0 into I. And let us find the magnetic field for this case. So to understand it better, let us consider this figure. So I have already drawn the Amperean loop, and when you see this toroid, you can have, that is, when you consider the turn, actually it is like this. That is, one current is entering the toroid or entering the loop and other current is leaving. So when you consider this Amperean loop, you can see that when you consider the turns which are lying within that Amperean loop, you can have only turns which are entering the loop, So here what happens, we don't have, when you consider the turns, portion of the turns within the Amperean loop, we have only turns, only portion of the turns which are entering only. So what will happen, all current are having the same magnitude. If I am giving plus I, let us take I as the current, and let us take plus I for current entering that loop and minus I for current leaving the loop. So if you have both the portion, then what will happen, the net will be 0. But when you consider this Amperean loop, you can see that we have only portion which are entering. So what will happen, all the current will be added up. So here we can write this equation as close. And one more thing, when you consider this Amperean loop, what is the direction of the magnetic field? Direction of the magnetic field is given by the tangent. Tangents drawn at points will give us the direction of the magnetic field, and dl is along the same direction So B and dl are along the same direction. So what will happen to B dot dl? It will become closed integral B dl, since they are along the same direction, angle between them, B dot dl is BDL cos theta. So BDL cos theta here is 0. Cos 0 is equal to mu 0 into I. Mu 0 into I. One more thing. This mu 0 into I is only for a single turn. When you have capital N turns, what is the total current? Total current is equal to mu 0 into capital N into I is the total current. So this equation will become closed integral B dl cos 0 is 1, which is equal to mu 0 N into I. In this equation, B is magnetic field, and you can see that the magnetic field B has got the same value at all the points which are lying on the surface of this Ampere loop at a distance r from the center. So it is a constant. At all these points we have the same value of magnetic field. So B is a constant. So constant is taken outside the integral sign. So it is B into closed integral dl is equal to mu 0 into Ni. Then what will we get after integrating this dl's? We will get the circumference of the circle. So after integrating dl, it is equivalent to the circumference of the circle, and it is equal to b into circumference is 2 pi into radius. Here radius is r, so it is 2 pi r is equal to mu 0 n I. Okay, then therefore magnetic field B is equal to mu 0 n by 2 pi r into I. This is the equation for magnetic field, and let n be the total number of turns per unit length. That is, n is equal to total number of turns per unit length, that is n is equal to capital N divided by 2 pi r. So we can also write this equation as B is equal to mu 0 Ni. This equation is just similar to the equation for magnetic field due to the solenoid, where n is equal to small n is equal to capital N by 2 pi r. So this is how we calculate the magnetic field for points lying inside the toroid, that is at this point. Now let us consider the next case, that is to find the magnetic field for points outside the toroid. Outside the toroid means that point lies here. It is outside the toroid. Then let us take that point as Q. Let the point be Q. Then as always we consider the Amperean loop, and it is a circle, again a circle of this distance, that is distance between that point and the center, can be taken as r3. Let us take that distance r3. Then for our convenience, let us consider this figure, that is this point lies outside, not point, this Amperean loop lies outside the toroid. Then you can see that for this case, for each turn, when you consider each turn of the toroid passes twice through the area enclosed by the Amperean loop. If you consider the area enclosed by this Amperean loop, each turn passes twice. Passes twice means that is like this. That is, you have portion of that turn which is entering, and you have one more portion of that turn which is leaving. So if I give the current for this as plus I, this is just opposite. So what is the sign given? Minus I. So what will be the total current for that single turn? It turns to 0. So here for this case you can see that the current coming out of the plane of the paper is cancelled by the current going into the plane of the paper. So the total current for this case is 0. That is, for this case I equal to 0. So closed integral b dot dl is equal to mu 0 I. Here current I equal to 0. So closed integral b, let us take this as b3 dot dl is equal to 0. So what happens here? b3, the magnetic field b3 is equal to 0. That is, for points outside the toroid, the magnetic field b3 equal to 0. So here for a toroid you have magnetic field only within the toroid. The magnetic field B has a value within the toroid only. For the other two cases, the magnetic field is 0. So this is how we calculate the magnetic field for a toroid and its 3 cases. Thank you.